Hello everyone, today we'll talk about the solution to the problem 2 keys keyboard. Feel free to pause the video and read the statement and we'll talk about the solution. First of all, one way of looking at what we can do, which might be useful for some solutions and it also is a good thing to confirm that we understand the allowed operations, is that if we start with some k characters at first and you want to generate p times k, we have to spend exactly p operations. Well, maybe it's possible to do it faster, but it's possible to do it in p steps. That's because we can select k and copy it, and then we can paste it p minus 1 times. So we have one operation plus p minus 1 operation, so that's p operations. That's useful because, well, it's clean to go from k to p times k. We can do it in p operations. Maybe it's possible to do it faster. So that's to make sure that we understand what we can do. Now, since we want to go from 1 to n, then it's clear there is something number theoretic about n that can inform us about the solution. For instance, often when you have problems with doubling and adding something, then we can look at the binary representation of our number and it will tell us exactly the number of steps. We just have to know how to interpret it. In this problem, of course, we do not have only doubling available. We have multiplication by any value. And as it turns out, since that multiplication, of course, leads us to thinking about how we can represent n as product of some integers. So, in other words, the prime factorization of n. Then indeed we can utilize the prime factorization of n to arrive at the solution. But that's not the solution I'm going to present today, but of course we'll talk about it. Now, another thing that's very common in situations like this is that we can think about dynamic programming. That's because we have this, let's say, this Dijkstra-like quality where we know how to get the value 1. We can do it in 0 steps. And since after every operation the number that we get can only get bigger and bigger, then if we know the best way to solve, for instance, to get some value n, then to get any value smaller, so we can only get values larger than n. And that means that we can take the smallest value that we have not yet processed, and we know that we cannot get it from any other values we haven't processed. So we can essentially start with 1, and starting with 1, and this is where the dynamic programming comes in. This is also similar to some coin changing questions, for instance. We know that we can copy that 1, and you can get a 2 in 2 steps, 3 in 3 steps, and so on. After that, we know the best way to get 2. So now from 2 we can go 2, we can go 4, 6, 8, and so on. And in fact, when we implement it, it's not even going to be quadratic. That's because if by starting with every element we go only through its multiples, then we have this sum of harmonic series times n operations, which is n log n. So it's not n squared, but it's n log n, and this is a standard pattern when it comes to multiplies. Well, multiples of numbers. And this is the solution that we're going to actually implement because it's the easiest solution and it's very clear that it works. So this is a standard dynamic programming. We start with some large infinite value for everything that we can achieve. We're only interested in numbers from 0 to n included. Well, we're not interested in 0, but we're just not going to use it. And of course, we can get the value 1 in 0 steps, because a single a is written already. And now we will just iterate over every value that can be generated, because in that case we're looking at the smallest value that we haven't processed already. We don't have to actually go past n divided by 2, because if we get something that's greater than n divided by 2, then we surely cannot arrive at n by copying and pasting it any number of times. And we're going to be trying to paste it twice, 3 times, 4 times, and so on, until we overshoot n. And in that case, if we need to copy and then paste with the total number of steps being steps, then we can get from start in steps to the value target. And maybe it's better than the previous best way of getting to the value target, in which case we remember it in the DP array. And of course, we now look at one step more, so a value is increased by start. And at the end, at dp of n we certainly have the best way of arriving at n, and this whole situation is in n log n. That's because while at first this internal while loop will be making essentially linear number of steps, but as start increases, then this loop will only go through all the multiples of start that do not exceed n, and there are about n divided by start such multiples. And so essentially, if we have a situation where we go n steps, then we go n over 2 because now our value is 2, then we have n over 3 because our value is 3, and so on. That's the same as n times, and this is the sum 1 plus 1 over 2 plus 1 over 3 plus and so on. This series 1 over I is the harmonic series, and that is about logarithm of n in total, that sum. And now I also mentioned that number theoretic thing, that we can look at something about n, about the prime factors of n, to arrive at the solution. And it's not exactly the same solution as our dp, because for instance in our dp we are trying to both take the number that we had previously and try to take it some number of times, and that number of times can be any multiple of it. So essentially we're looking at all the multiples, and in particular we're looking at composite multiples. So for instance we can start at 3 and trying to go 13, well 13 is not a good idea, 12 steps from 3 to 36. But we might come up with the idea that it's not good to do very many steps along the way, and it's best to make all those runs of pasting shorter and shorter and shorter. However, of course, we also do not want to make unnecessary copies. And the sweet spot would be to only look at prime numbers. That's because if we know that our number a is equal to some prime p times the number b, then, or in general, even if we have n and n is equal to some a times b, then we can generate it with the number of steps necessary to generate a plus the number of times necessary to generate b, because we can generate a normally and now treat a as a single block and do the same thing as we would to generate b, starting with only a single letter. Or we can generate b and then generate a times b, following the process to generate a. And as it turns out, as long as we only stick to prime numbers, then we will get to an optimal solution, and in that case, of course, it doesn't matter the order in which we do it. It's clear, of course, that those operations are of this form, a times b, where a and b are integers. It's not that clear why doing it always by taking prime factors is the best solution. So if you want to go with that idea, then you need to be able to prove it, especially since you also want to be sure that this solution works. So this solution is better because it's still short. It's n log n instead of n squared, so that's also good. And you can be sure that it works. But if you like number theory, if you like prime numbers, then feel free to also talk about the greedy solution if somebody asks you a question like this.